Now let us go to the second type of integrals, real integrals, which can be obtained by residue theorem. These integrals will be of the kind, let's call them j. So j will be in the form integral of f of x dx with limits on x being minus infinity to plus infinity. And note that here f of x is a real function, and more importantly it is a rational function. So a one polynomial upon other polynomial. Okay, now how are we going to interpret this? Okay, so usually what we do is we split this particular interval of integration at any convenient point, okay, in between the limits. So let's choose it to be 0. Okay, so once we complete the integration process, the indefinite integration, that is antiderivative, then instead of substituting minus infinity straight away, you just let it as a and take the limit of that as a tends to minus infinity. Okay, and same thing applies to the upper limit. Okay, so you may write it as integral f of x dx from 0 to b as b tends to infinity. Okay, and these two integrals will exist provided both the limits exist. Okay, so this is how we interpret this particular integral. Okay, now while applying the technique of contour integration or residue integration, we are going to make some assumptions, and well, these assumptions will be fulfilled by the integrants. Okay, assumption number 1, the denominator of the function f of x is never equal to 0 for all x in the set of real numbers. That means the denominator doesn't have real roots, or should not have. Okay, so this provides us automatically some of the possibilities. So you may have x squared plus 1, x4 plus 1. So in general, x to the power any even number, positive even number plus 1. Okay, fine. And the second assumption is more important perhaps. The degree of the denominator is at least greater than the degree of the numerator by 2. Okay, so this is the second assumption. This is required to, well, this is required in the method. That's all you can say at this stage. Okay, there are reasons for that, of course. All right. Now, what is the implication of these assumptions? Yes, what is the implication? The implication is that the limits exist, and you can now actually introduce a single real variable r, and you can combine them and say that if r tends to infinity, then this integral will be, or j will be equal to limit as r tends to infinity of the integral f of x with respect to x from minus r to r. Okay, so there is no need to write two separate limits. Okay, so this is as far as the real integrals are concerned. Let us now bring in the residue theorem. Okay, now because we have assumed that f of x is rational, we can be 100% sure that f of z has finitely many poles, and we'll only consider the upper half plane. Imaginary part of z positive. Okay, all right. Now what I'll do is, or what we usually do is, we have to choose a sufficiently large value of r, which is the radius of this semicircle, which encloses all the poles. Okay, which means we should cover all the poles of the function f of z which lie in the, well, in the first or in the second quadrants. Okay, and this is made sure by choosing a very large value of r. Okay, so we now cleverly build a contour, okay, a semicircular contour whose diameter part coincides with the x-axis. Okay, so this is going to be the integral associated with the real variable x. Okay, because there is no imaginary part. And if you call the entire I would say semicircle as C, then, or entire contour of integration as C, then what we want is minus r to r. Okay, and to this we need to add the semicircular region, okay, or semicircular curve. Okay, so this will be a contour integral. So we may now write it as integral of f of z dz along C, taken anti-clockwise, traverse anti-clockwise, will be equal to integral of the function f of z taken along S, okay, this one, plus the integral of the real variable x, okay, because we are now on the real axis, from minus r to r f of x dx. Okay, now we are not going to prove this, but you can actually prove that by the ML inequality, if we take r, or if we let r to tend to infinity, the integral along the semicircular arc tends to 0. Okay, due to the appearance of the term 1 upon r in its bounds. Okay, so if this integral tends to 0, then the required integral, that is integral of f from minus infinity to plus infinity, is actually this. Yes, and we know how to find it. Okay, it is 2 pi I into sum of the residues of f of z inside the closed contour. Okay, so here we need to make sure that we consider all those poles which lie in the upper half plane. Okay, now the use of semicircle is deliberate here. There is no need to consider the full circle, because we want some of the contours portion to be there on the real axis. Okay, so you can think of an expanding semicircle whose center is at the origin, and we always take the diameter of that semicircle to be along the x-axis. Okay, fine. So this gives us explicit formula to find j, which is 2 pi I times sum of the residues of the function f of z at all those poles which lie in the first or in the second quadrants. Okay, now we are going to solve this famous integral using residue theorem. Okay, so this integral is 0 to infinity 1 upon 1 plus x to the power 4 with respect to x, and you have to show that it is equal to pi by 2 root 2. Okay, now the immediate question that you would ask is, here the lower limit is 0, and in the discussion it was minus infinity, so how are we going to do this? Okay, note that this is an even function, because this is a real variable function. We will now say that this is an even function. So this integral is actually 1 upon 2 times the same integral being evaluated from minus infinity to plus infinity. So if we manage to prove that the integral's value from minus infinity to plus infinity is pi by root 2, it automatically solves this problem. Okay, all right, we'll make sure whether our assumptions are satisfied. There are no real roots of the denominator. Yes, it has 4 roots. Okay, so you have to now find the apply the de Moivre's theorem or the Euler's formula to get the roots. But as far as possible, I mean, we can at the very first glance we can say that x to the power 4 plus 1 equal to 0 cannot have any real roots. Okay, so the first assumption is satisfied. Degree of the denominator is 4, degree of the numerator is 0, so there is at least a difference of 2 between the 2 degrees. Yes, okay, so the assumptions are satisfied. Let's now calculate the zeros of f of z. Oh, sorry, I should not have said the f of z. Let's calculate the zeros of the denominator of f of z. Okay, which is 1 plus z to the power 4. Okay, use the complex exponential representation of minus 1. which is e to the power I pi, and now use the periodicity of trigonometric functions and write it as e to the power I times pi plus 2n pi. Okay, so z is now going to be e to the power I into pi plus 2n pi upon 4, the standard process that we use to solve the equations. Okay, so n can now take 0, 1, 2, 3. If n takes the value 4, it will come back to 0. Okay, you know that. Now we need to identify only those roots for which the imaginary part is greater than 0. Okay, because we are considering this semicircle so that the interior of the semicircle lies only in the first and the second quadrants, which covers the positive imaginary axis. Okay, so we will not consider the roots in the third and the fourth quadrants. Okay, so the first root is now e to the power I pi by 4, first quadrant, and e to the power I 3 pi by 4, right? For 3 pi by 4 you need to take the value of n as 1, so it is pi by 4 plus pi by 2, so 3 pi by 4 or 135 degrees, so clearly in the second quadrant. And due to the symmetry, the other two roots will be e to the power I minus pi by 4 and e to the power I minus 3 pi by 4, which should not be considered. Okay, so the integral j, for which the limits are minus infinity to plus infinity, will be 2 pi I times the residue at e to the power I pi by 4 plus residue at e to the power I 3 pi by 4. Okay, now we have actually solved this problem in our discussion, okay, on the calculation of residues, and now we are going to use the L'Hospital's rule. Because the residue at e to the power I pi by 4 will be limit as z tends to e to the power I pi by 4 of z minus e to the power I pi by 4 upon z to the power 4 plus 1. Okay, now because e to the power I pi by 4 is a root, both the numerator and the denominator will go to 0, so this is now in the indeterminate form 0 by 0. Differentiate. Numerator 1, denominator 4z cube, so the residue will be 1 upon 4z cube at that particular pole. Okay, and see, this not only applies to e to the power I pi by 4 but also to all other 3 poles as well, but we need only 2 of them. Okay, so you have to now substitute z as e to the power I pi by 4 and e to the power I 3 pi by 4. Okay, but you are cubing it and plus it is in the denominator, so multiply the power by minus 3. So it will be minus 3 pi by 4 for the first and minus 9 pi by 4 for the second. Okay, and you use the Euler's formula now, e to the power I theta is cos theta plus I sin theta. Okay, what you can do is you can take this 1 upon 4 outside, so it will be 2 pi I by 4 or pi I by 2. Expand. Cos of minus 3 pi by 4 is minus 1 upon root 2, and same is the sign because it is in the third quadrant. Okay, e to the power I minus 9 pi by 4. Okay, now write minus 9 pi by 4 as minus 2 pi minus pi by 4. So it is as good as taking minus pi by 4. Cos of minus theta is cos theta, so 1 upon root 2. Sin of minus theta is minus sin theta, so minus 1 upon root 2 I. So the imaginary parts, I guess, will get cancelled. Yes. Oh, sorry, not the imaginary parts. The real parts will get cancelled. Sorry. Minus 1 upon root 2 plus 1 upon root 2. And the imaginary parts will actually get added to minus 2 upon root 2 times I. Okay, fine. Let's also not forget pi I by 2. I squared will be minus 1. First, let's cancel 2. I squared will be minus 1, so I into minus I will be 1, so it is pi by root 2. Okay, and due to the even parity of the function f of x, the given integral will be j upon 2 as discussed earlier, which is pi upon 2 root 2. Okay, and is it what we wanted to prove? Yes, the integral is pi upon 2 root 2. Okay, so now we have seen how we can find the improper integrals of one kind with the help of residue theorem by considering the closed contour C, which is a semicircle whose radius is denoted by r, and we usually we have to let r to tend to infinity, so that the value of the contour integral along the semicircular arc which is present in the complex plane, it tends to 0 by the ML inequality. Although we have not yet proved this result, well, trust me, it is true. Okay, fine. So this is how we can calculate improper real integrals using residue theorem.